So in video 3 on acids and bases, we're first going to talk about the autoionization of water. Remember, water could act as both an acid and a base, and we get some ions with just pure water in solution. We'll talk about the significance of that K value as well. And then we're going to go into pH calculations. We'll find out what that actually means, how to calculate them from the numbers that we can get from simple ice charts. So remember, we talked about water being amphoteric. It could act as both an acid and a base. So if I have pure water and two molecules of it are together, I could actually get an equilibrium to where one of the water molecules acts as a base and goes to the conjugate acid hydronium ion, and the other water donates the proton, acts as an acid, and becomes the conjugate base, the hydroxide ion. This is referred to as the autoionization of water, and the products are both hydronium ion and hydroxide ion. And if you look at this reaction, I can write a K for this autoionization of water. Remember, pure liquids are not included, so it would only include the aqueous ions, hydronium ion and hydroxide ion concentration in that K value. And we could see on the next slide that equilibrium expression would be the hydronium ion concentration times the hydroxide ion concentration. And this is a very special number. It's so special that we don't use Kc or Keq for it. We give it its own number. We're calling it Kw, and this is known as the ion product constant for water. And at 25 degrees, it has a specific value, 1.0 times 10 to the minus 14. So we could see again, this equilibrium, we don't have tons of hydronium ions and tons of hydroxide ions in solution. It's a very small number, so the reaction lies heavily on the water side, and there's not that many ions present in water. So the pH scale, for those of you that are taking analysis 1, I'm sure you covered this by now. The log scale, we're dealing with the log base 10 scale now. If we take the negative log of the hydronium ion concentration, we're defining that as the pH. So the H would stand for the H plus, and the P actually stands for the negative log of that. So when we do that, we can calculate the pH. So again, let's go back to this Kw for a second. So it has a specific value, 1.0 times 10 to the minus 14th. And I'm going to form equal amounts of H3O plus and OH minus when water autoionizes. So because in pure water these two concentrations are equal to each other, my acid concentration is going to be the square root of that Kw, or 1.0 times 10 to the minus 7 molar in concentration. And if I take the negative log of that acid concentration, or take the pH of it, I wind up seeing that water has a pH of 7, and no surprise, this is something that you learned in biology class, and now we're seeing how it works out mathematically. So again, you remember that anything that has a higher acid concentration, anything that would be above 1.0 times 10 to the minus 7, would have a low pH, so it would be less than 7. Again, neutral, if it's actually 1.0 times 10 to the minus 7, I get a pH that's equal to 7, and for a base, I'm going to have a much lower acid concentration. It'll be less than 1.0 times 10 to the minus 7, and my pH will result in a pH greater than 7 for that. So this P in pH just tells us to take the negative log. There's nothing special about it. It's just, think of it as a function. When I see P in front of something, I take the negative log of it. So I could take the POH, I could take the PKW, and both of those just mean the negative log of it. I could P anything, mathematically speaking. Okay. So because the hydronium ion concentration times the hydroxide ion concentration equals this Kw, right? And using some rules of logs, I know that I could take that value, and if I take the negative log of this product, it's really like doing the addition of each of these. Remember, if I take a product, when I take the log of a product, it becomes the addition. So it's really the negative log of the acid concentration plus the negative log of the hydroxide ion concentration equals the negative log of the Kw. So this negative log of the Kw is the pKw, which equals 14. And these become pH and pOH. So I could see that for any system in water, the pH plus the pOH is going to equal 14. So if I know one value, if I could calculate the pOH, I could just move this over and solve for the pH of my system. Okay, we got to pay careful attention to sig figs with logs, and it's a little tricky. Remember, we talked about a product of something being like an addition. So if I take the negative log of something that has a number before the scientific notation exponent, I could split that up. So the negative log of this number is really like taking the negative log of 2.3 and the negative log of 10 to the minus fifth. So this number actually gives us one significant figure. The exponent, when I take the base 10 log of that, will give me, and the negative log of that would give me 5. And this number, I actually get a decimal. So this two-digit number provides me the two significant figures after the decimal place. My coefficient gives me my number before the decimal place happens. So if I look at it this way, I actually create, in doing the math for the logs, an additional significant figure. I go from this number, which has two significant figures, and because of this placeholder exponent, I wind up with a number that has three significant figures in it. Okay, so how do we measure the pH? We've already done this before. We've done a titration reaction. We used phenolphthalein as our indicator, and we saw the color change. It goes from colorless on the acidic side to the pale pink that we want to see when we go to the basic side. There are a lot of other indicators, and depending on which pH range you need to measure in, you'll use the appropriate indicator. Other methods, we can use litmus paper. You've probably done this in bio before. If something is red litmus paper will turn blue if I have a high pH, and blue litmus paper will turn red if I have a lower pH. The better way to do this is to use a pH meter, and here's a semi-fancy one. There's some that are even, that look just like pencils, that are kind of simpler to operate. And what it does is it actually measures the voltage of the solution. So it's really measuring ions in solution. It's measuring hydronium ion concentration, and that voltage across that solution is what's being measured, and we can convert that to the ions and get a pH reading. Okay, so here's a list of some common household items that you'll find. You see that blood and tears, which is a common thing in chemistry, I guess, is a little bit on the basic side. Things like black coffee are on the acidic side, or on the acidic side of this.